Here's our second example of using using conservation of energy to solve problems. So now I have a child on a slide. He's climbed up and he's going to slide down. And my question is, how fast, if he starts from rest, how fast is he going at the end of the slide? In other words, when he comes down here and pops off the slide, how fast is he going right before he impacts the ground? Hopefully he's okay. So the slide is he starts out at a height h and he ends up down here on the ground. Okay, so the first thing to do if I know I'm going to use conservation of energy is to set my 0.4 potential energy. And it certainly seems reasonable to me to set it here on the ground. Again, do you have to do that? Absolutely not. But I'm going to, and I think the reasons will be made clear. Now, let me point out that you can do this with kinematics, right? If you know the angle of this, you can determine then the amount of gravity acting down the slide. This is just like an inclined plane problem. Gravity, gravity is going to be acting down. You're going to resolve that into a perpendicular component and a parallel component. You can solve for the parallel component. You're going to get g sine theta, you're going to get mg sine theta. And that's going to tell you that g sine theta is the acceleration in that direction. And you can do this if you know a couple things about, how far down you go, or you might have to solve a system of equations. You can do it, but it is a significant amount of work, and I would need to give you a couple more things here. What I hope to show you is that with energy, this is actually somewhat of a trivial problem. So let's do it. Let's write down the conservation of energy. Initial kinetic plus initial potential plus work due to non-conservative forces is then equal to final kinetic plus final potential, not initial, final, right? The amount of kinetic and potential energy I start with plus the amount of energy I lose or gain due to any external work has got to equal to kinetic and potential final, my final energy content. Okay, so let's see what we can get rid of. Well, if I am starting from rest, which I said I was, my initial kinetic energy is 0. 1/2 m times 0 squared just becomes, 0. If there's no friction on the slide, and then maybe I should make that explicit, this is frictionless slide, right? The holy grail of childhood. Then there's no work due to non-conservative forces. I'm ignoring air resistance. There's no friction. All I have is gravity. That's going to be 0. If I set my 0 point here where the child gets on the ground, then my final potential energy, mgh, is mg times 0. That is just 0. And it certainly looks like this is shaping up nicely. My initial potential then, if I'm at a height h, I know what that is. That's gravitational potential, mgh. And that's going to be equal to what I have left over here, 1/2 mv final squared. Okay, looks like my m's are going to cancel. Looks like I'm going to multiply both sides by a 2 and take a square root. V final is root 2 gh. And if you go, hey, I've seen that before. Yes, you have, because you watched the previous video. That's the same result I got from dropping a ball off a building straight down. That's really interesting. Now, does this happen in real life? Probably not, because there's no such thing as a actually frictionless slide. But I want to point out, if something is really close to being frictionless, then this is a pretty good approximation. This was not much work, right? It certainly is a lot less work than getting this answer with kinematics. Can I do it with kinematics? Absolutely. Do I want to? No, I do not. This is much more straightforward. Now, of course, energy is not a vector. And so what I have here is a speed, not a velocity. I believe I've been saying the word velocity, and that's, forgive me for that. This is a speed because I don't have directional information here. If I need a direction, I either have to get it from some sort of inspection here, although it's probably not hard to see. In this case, I get it, down the ramp. Or I have to use kinematics because kinematics involve vectors. I don't have vectors here, but it does allow me to get the speed really easily, and I can probably get the direction, if I need it, from some sort of inspection of my physical situation. So in this case, it was really easy to do a somewhat complicated problem using energy considerations.